Okay, hello. So hopefully this is working, but today I'm going to be explaining how to do the pumpkin drop lab from Mr. Pabico's physics class. So this is like my first video in a while, mainly because I'm in college now. But I remember when we did this project last year, we didn't end up actually getting to do it, and I've had some questions about this specific project and how you really like calculate stuff. So I'm gonna just make a video to clear up some things. So basically the goal of the project is you're gonna have like a little pumpkin thingy. I'm really bad at drawing with this, I'm sorry. Here's your little pumpkin thing. And so you're gonna make a string out of rubber bands so that when you attach this pumpkin here and you're given a height h, you know how many rubber bands you need to basically make it get really, really close to the ground but not hit the ground and explode. So how you do this is basically first you start off with a single rubber band, and you're going to take your little spring scale and you're going to measure with your spring scale. It's like a plunger and I can show the amount of newtons. You're going to measure how many newtons it takes to stretch the springs, or to stretch the rubber band, sorry, a certain distance, and probably just do this like a few centimeters. But basically then you're going to use the equation F equals negative kx to determine basically the spring constant k. And so I'm not going to like write in values, but it should be like, I don't know, like 20 newtons per 5 centimeters or something. But basically once you get your k value of a single rubber band, I'll just label that as k1. Basically you can use this to determine basically the the rest of the problem. What am I even getting at? Anyways, so basically how this is going to work is you're going to be given a height off the ground, and you're going to have your little string here. You're going to already have calculated this, let's say hypothetically, and you're going to have a mass. And so basically what's going to happen is this is going to fall in free fall, basically, just accelerating with gravity until your string is fully stretched out. And so after it's completely stretched out without having any elasticity, sorry, I guess it wouldn't be stretched at all, but once it's completely unraveled, then it'll start stretching. And that's where your spring force is going to come in until when it reaches a height of 0, you're going to get no motion here. So the velocity will be 0. So basically what this is saying is it's going to be stretching a distance of x. This is our stretch distance. And our initial height is basically just going to be the top. And so we can see that all of the gravitational potential energy is being converted into spring energy, because there is the intermediate phase where it has kinetic energy in the form of its velocity, basically, like right here, it's going to be moving pretty fast, and then at the bottom the velocity also equals 0 though, so we don't have to worry about kinetic energy. So it's a very simple equation to set up, basically. Okay, I'll clear the board. So basically we're starting with mgh, which is gravitational potential energy, and you're going to be given the mass and the height, right? So this is given, and you want to calculate basically how many rubber bands you're going to need. And so this is somewhat difficult, but for now I'll just write out spring energy. So 1/2 kx squared. So to do this, we have to think about what the x even means. So I'll redraw this diagram just as it's fully stretched out. So we have this entire h, right? And here's our mass still. Can say up is positive, who really cares? Basically, this mass is going to have a velocity of 0, and it's going to have stretched a certain distance with the string, and that distance is going to be x. But you can't really find out what your x is going to be because it completely depends on the force that the mass is, or I guess the force that the spring is exerting, and the spring constant. And you can calculate your spring constant, k, but calculating like the force at any given moment is going to be kind of difficult. So instead, let's think about what this length is. So this length is actually going to be the length of your string, or rubber band. So if we think of height in terms of string length and stretch length, we get the following relationship, which is h equals L plus x, and then we'll find that x equals h minus L. So now that we have this, we're given this, and we're going to adjust for this. This is basically going to be what we're solving for, the length of string. So now we're going to just take this, and we're going to plug it in there. So then we get mgh equals 1/2 k h minus L squared. So basically I could solve for L. That's basically what you're going to be doing. But let's take a little bit of a break from this and figure out what our k value is going to be. Because we've already discussed that our k1 value will be the spring constant of one rubber band. But if you have an entire chain of rubber bands, it's not going to be like that. So let's say, hypothetically, just for simplicity, your chains are probably going to be different than this. My chain was different than this. Let's say we just have rubber bands connected end to end, like this, right? So we know some of these spring constant rules, right? Like when you have, what are these called? In sequence, springs in sequence. Basically, 1 over k total equals each of the separate rubber bands. You cannot see what this is saying, sorry. This is supposed to be k1. So basically the number of rubber bands is going to be the number of 1 over k1s we're adding. And if you think of this, as this goes on and on, this will eventually lead you to n over k1, if you have them all in a sequence. So after you've done that, you can basically solve for the k total as inverting that k of the original rubber band, I'll draw this little one better, over the number of rubber bands. Sorry if I didn't say it, but n I'm just using as number of rubber bands. So now we can put this back into here, assuming that we have like a length of rubber bands, or string of rubber bands, one rubber band connected to the other. But this gives us now two variables that we don't know, because we don't know the number of rubber bands and we don't know the length. So we're going to have to relate them to each other. So if we think about it, a rubber band relaxed will have some length. How about I call it little l, right? It has some length, and so basically to relate number of rubber bands to big length, it's basically going to be the number of rubber bands times the length of a single rubber band, probably in meters if your height is in meters, and then that's going to equal L. So then, finally, if we write out our full expression, we'll have mgh equals 1/2 k1 over n times h minus n times L. I guess that doesn't really look like L. Maybe look like that. That doesn't look like L either. More subtle. That looks like an integral. We have this squared. So now we only have one variable, which is n, and the rest is given. But let's just check to make sure that we'll know every single thing. So mass is going to be given. Gravity, we know gravity. Height is going to be given during the day. Our spring constant, we should have that measured. Spring constant of a single rubber band. Number of rubber bands is what we're solving for, and we know height. So all of our constants are basically known, and we're just solving for our variable n based on these. I guess they're not. I guess it would be a function of h versus n. But regardless, now I'll give a little sneak peek of how to solve this. So, I'm not really... Anyways, I guess I'll clear this because I kind of have way too much stuff. And I'll rewrite our whole equation out. Equals, what did I say, 1/2 k over n times h minus n L squared. So, if we do a little bit of algebraic manipulation, we can, maybe let's do this step by step. This turns into 2 mgh, that equals to k1 over n, and I'm going to do 2 steps in one. I'm going to distribute the square to all these, so I'll give us h squared minus 2h n L plus n squared L squared. Okay, and that's just, I don't even know, distributive property, whatever. So now what we can do is we could even just get this k out of here as our next step. So we get 2 mgh over k1. And this is going to be equal to, I'm going to distribute the n to each value. So that's h squared over n minus, so n divided by n in here, I'm not going to write out the n, it cancels. So you get 2h, and that's, I guess, my L. And then we're adding n divided by n, the power cancels, we get n L squared. I don't know why I wrote L so differently, both of these, whatever. So basically now you might be like, oh, how do I solve this? It's not a real quadratic. Well, technically it is. It's just you have a -1 power here, and you have a single power and a power of 0. But what you can do is you can multiply everything by n, but before I do that, I'm going to just move this to the other side. So our next step will be solving for 0, basically. So we have h squared over n minus, I'll put all these into one big thing. So we have our negative 2HL. I'm going to just write the L as a line. And then this we're subtracting to the other side, so that's also going to be negative, but I'm going to leave the negative on the outside, so technically it's plus here. 2mgh over k1. And then, as a final step, I'm going to add this NL squared. And for simplicity, I'll just multiply everything by n. So we'll have n, and then n. So basically these two cancel. We have our 0 degree, our first degree, and our second degree, full quadratic formula. And so basically you'll get, I guess this means you will get two values of n. As for what they each mean, I honestly don't want to have to think about that. Probably one of them might be like, because it's going to be like a whole line, huh? Probably pick like, oof, I don't actually know. Well, you'll probably have to do a little bit of interpretation on your data. But once you plug it into the co-op form where this is C, B, and A, you'll find the N, or the number of rubber bands. However, your spring constant probably is going to be a lot more complicated than this, than just like whatever K over N. Simply because that's if you have a string of rubber bands. I'd advise against doing that because, you know, rubber bands aren't ideal springs. And so that means they won't stretch proportionally like they roughly do, but I feel like the more stretching you're doing to a rubber band, the less force it might, the less experimental force it might give. So you might want to consider having a rope that's basically like completely sturdy, and then it's only going to stretch like, I don't know, like this. Because if you have rubber bands like all the way, like, what am I trying to say? If you just have them like strung together like one rubber band tied to the next, and especially if they're weak rubber bands, you're probably gonna get something looking more like this, where it stretches for like most of the way. And the more stretching you have, the more room there is for error. Just because we're not using like ideal sort of springs. So yeah, but that's basically gonna be it. This is just like an example of how you would do it. Don't like try and plug your values into here, because that probably won't work, and I might have done my algebra wrong. If there's any questions you have, feel free to comment them. And if I did anything wrong, or if you think I did anything wrong, just let me know. I probably did. But this is just like a general like video just for like reference if you're struggling with this project. But yeah, let me know also if you want me to do any problems like this in the future, if you have any like specific questions. My videos from the past do cover basically like all of the exam topics from, I feel like, this point onward. So I think watching those will probably be helpful. But yeah, if you have any problems you need me to solve or any questions, just let me know. See you later.